Okay, so I'm recording now for posterity, so everybody can learn this wonderful material. Okay, so not red. Been marking problems from chapter 9. How are you guys holding up? You doing okay?
Yeah, pretty good. Yourself?
Yeah, surviving. It's okay.
I have some problem with Sigma,
Mm-hmm.
but yeah, I'm okay with the rest. Like I found it more difficult than the rest of the notion. That's all.
Yeah,
So
I would agree. I agree with that. I agree that the Sigma notation is a bit trickier. So yeah, I'll be doing problems that come from the list for sure. Um, yeah, I absolutely. Okay, so let's start with a few really basic ones. So here I'm on page 232 of the book. So number 20. I'll go over that quickly. So we have vectors, or u is 2 minus 1 0 minus 3. Notice that, so in some instances we write vectors with round brackets, sometimes it's with pointy brackets. It makes no difference. V is 1 minus 1 minus 1 3, and W is 1 3 minus 2 2. 1 3 minus 2 2. So we're given these three vectors and we're asked to evaluate some expressions which are built from those two basic operations we have on vectors, which are sum of vectors and multiplication by a scalar. So I'm going to do D. Okay, so if you can figure out D, all the other ones should be exactly the same. There's no extra difficulty. So I'm asked to find 5u minus 3v minus 4w. So let's see. Yeah. Here we go. So this is 5 times 2 minus 1, 0 minus 3, minus 3 times 1 minus 1 minus 1, 3, minus 4w. So this is minus 4 times 1, 3, minus 2, 2. So this is 10 minus 5, 0 minus 15. Since I can keep the minus sign. I can keep the minus sign outside or just bring everything in. That's what I'll do. So this is plus minus 3, 3, 3, minus 9. Be careful with the signs when you're doing this. Obviously, if you go too fast, you will mess up a sign. Everybody does. Plus minus 4, minus 12, 8, minus 8. And so finally, I add these together. You can do it two at a time, or you can just do it in one shot. So here it's 10 minus 7 is 3. Then minus 2, that's minus 14. Please check my arithmetic. 3 and 8 is 11. And this is minus 24 minus 32, I think. Hopefully this is correct. I'll just check the answer quickly. That's 20D. Yes, got it. Okay. All right. So all the others are exactly the same. Let's see. Let's do number So, of course, if you have any questions at any point, just let me know.
Yeah, I have one, sir.
Yep.
Pardon to interrupt, but yeah, so it was -3 times what's inside the parentheses, but the -3 became plus.
Okay, so I'm multiplying. So I'm multiplying the vector 1 minus 1 minus 1 3 by -3. So okay, let's just do one little remark here. I'll put it in blue. This here. Okay, so I've got -3 times 1 minus 1 minus 1 3. Of course, do you agree this is the same as this? -3 3 3 minus 9. You're okay with that?
Yeah, absolutely,
Okay.
yeah.
Yeah. So, but if I have, let's say, some vector, I'll try to use. Okay. So I have 5. Wait, I don't want to. So I've got 10 minus 5 0 minus 15 minus 3 times 1 minus 1 minus 1 3. This is the same as 10 minus 5 0 minus 15 plus minus 3 times 1 minus 1 minus 1 3. Do you agree with this also? Right, subtracting is the same as plus the minus what's after, right?
Okay, so if I get this straight, so because you put a plus in between,
Mm-hmm.
the rest also changes the sign, right? So -3.
Yeah. So
1. Okay.
yeah. So subtracting. Okay. So look, a vector A minus a vector B. This is the same as A plus the vector minus B.
Oh, okay.
Right.
I see.
So that's why when I have this minus there, what I did is I could have multiplied the vector 1 minus 1 minus 1 3 by 3 and kept a subtraction in between. I could have done that, right? It's either or. If you're more comfortable with doing
Okay.
that, that's fine. But what I did is I multiplied the whole thing by -3, but of course it won't be a minus outside, it has to be a plus, right? Because
Okay,
of
thank you, sir.
this. Does that, yeah, it does make
Yeah,
sense?
yeah.
Okay,
It
good.
does make sense. Thank you.
All right, excellent. Okay, so let's go here. Okay, this is a number. Okay, let's do number 26. So then I'll be doing a few things at the same. No, let's okay, wait. Let's do number 25 first. I'll do number 25. That's a bit big. C. Okay. So 25C, I'm asked to compute D transpose A transpose. Okay, so there's a few things going on here. Okay, so I'm going to look up what the matrices are. So the matrix A is 1 minus 1 2 0 3 4. Now again, curved brackets, square brackets, same thing. Okay, so that's the matrix A. The matrix D is the matrix 2 minus 1 3 2 minus 1 3. So this is a 2 by 3 matrix, right? That's the size. This is a 3 by 1 matrix. Okay, so these are the two matrices. So what's the transpose? Again, the transpose is rows become columns. Okay, so first I'm going to compute A transpose. So this is a 3 by 2 matrix. First row becomes first column, 1 minus 1 2, and then 0 3 4. Okay, so again, it's just a question of knowing what this means. Once you know what it means, there it's a no-brainer, right? So that's all there is to it. The transpose of D, D is a 3x1 matrix, so the transpose will be a 1x3 matrix. And so this is 2 minus 1, 3. So these are the two transposes. And then I'm asked to compute D transpose times A transpose. Let's at least check if it makes any sense, right? So D transpose is a 3x1 matrix. And A transpose is a 3x2. Did I choose? Okay, so D transpose A transpose. This is a 3x1, and this is a 3x2.
Wouldn't A be a 2x3?
Sorry, which one?
Wouldn't A2 be a 2x3 matrix?
No, 3x2. So it's a number of rows times number of columns.
But then why is DT 3 times 1?
Sorry, why is which, what?
DT, why is DT 3x1?
Because I messed up. Yes, thank you. That's the reason. It's a 1x3. Duh. Yes, thank you. Okay, so yes, so it's a 1x3. So that'll help. Gee whiz. 1x3, 3x2. These numbers are the same. Thank you. So I was.
Sir,
Yep.
pardon.
Yeah.
So the transpose is always written this way, like a power to the power of t, right?
Yeah, I mean it's a notation. It's not a. I mean it's not a power in the sense of multiplication.
Like written like
Exponent as an exponent.
okay.
Yes.
Okay.
Yes. Yes.
Okay.
Yes. Yeah. Okay. So D transpose is a 1x3 matrix. A transpose is a 3x2 matrix. Those two values are the same. So this is a legit product, and it's a 1x2 product, right? So it's a 1x2. So I have to figure out what these guys are. Okay. So I'm going to write it out this way. So this is D transpose 2 minus 1, 3 times A transpose, which is 1 minus 1, 2, 0, 3, 4. And so when I multiply, it's row times column, right? Row 1, column 1, that'll give me this answer here. And then this row times this column will be my answer here. Okay, so 2 times 1 minus 1 times minus 1, that's a plus, plus 3 times 2, so this is, that's 9, right? And the other one is 0 minus 3 plus 12, that should be 11, unless I messed up. That should be okay. 2 times 0 plus minus 1 times 3 plus 3 times 4. That's the second one. Let me just check that answer. So this is 25C. Okay. Yeah, 12 minus 3 is 9. Thank you. So that's 9. So I messed up. And now I'm good. Yes. Is that okay? Doing arithmetic live like that is harder than it looks.
Sir,
Okay. Yep.
one of the web works, we were asked to see the size of two matrices
Mm-hmm.
and then say whether one of them is undefined. If it's undefined, just write undefined
Yep.
and give the resultant size, if I may say this way.
Mm-hmm.
And for some reason, I've written just like it was. One matrix was 8 by 3, and the second one was 3 by 2. So we could do A times B
Mm-hmm.
because, you know,
Yep.
the column is 3 and the row
Yep.
of the second one is 3. So I gave the size as 8 by 2.
That's
and
correct.
It gave me that it was a wrong answer.
Okay. The way you're telling me the problem, you did it right. So
Yeah.
it's fine. So
Exactly.
either it's the way you wrote it, or maybe they switched the names of the. I mean, I'd have to
one
see
of
it.
them I've written undefined, and it was the right answer because they give me 50%. And then the second one, I just written 8x 2.
Mhm.
And then I even tried with a capital X, and it didn't work. It said the answer was
Okay. Once I'm done with these problems, show me the question.
Okay.
Okay, we'll
Thank
take a
you.
look at the question, because the way you're describing it, you're right. I mean, it's clear.
Thank you,
Okay.
sir. Thank you.
All right. Okay, let's go take a look at number 26. Okay, so I've got the matrix A, which is 2, 2, 3, minus 1. I'm asked to find, oh boy, okay. Find A squared and A cubed. And I'll do B. Okay, B. And F of A, where f of x is x cubed minus 3x squared minus 2x minus 2x plus 4. Okay, so notice, by the way, that to compute f of a, I'll have to compute a squared and a cubed anyway, so it's not extra work by to do those. Okay, so let's start with a squared. What is a squared? That's a times a, and you can always multiply square matrices by themselves. That's always, the sizes will always match. So this is 8. 2 times 2 is 4, minus 2 is 2. That's 6 minus 3, that's 3. And 6 plus 1 is 7. Please make sure that I did it right, because if I mess up at the beginning, everything's going to be messed up after. So let's check that out again. Okay, so this row times this column, this is 4 plus, okay, so then I messed it up. My brain is not working well this afternoon. Bad brain. So this is 4 and 6 is 10. Yes. Let's do this row times this column. So that's 4 minus 2, that's 2. That looks okay. Then this row times this column, that's 6 minus 3, that's 3. And then 6 plus 1 is 7. So hopefully that's okay. Okay. Let me cheat so that I don't go down a rabbit hole after that. That's number 26. Okay, that's good. So a squared is good. A cubed. So what is a cubed? It's a times a times a, or if you prefer a squared times a, or if you prefer a times a squared, it's all the same. Okay, so I'll do just 2, 2, 3 minus 1 times 10, 2, 3, 7. You see that if you messed up a squared, a cubed is going to be messed up too. So that's 20 plus 6, that's 26. That's 4 plus 14, that's 18. This is 30 minus 3, which is 27. This is 6 minus 7, which is minus 1. Let's make sure this is correct. So this row times this column, 20 plus 6 is 26. This row times this column, that's 4 plus 14, that's 18. Then 30 minus 3 is 27. And 6 minus 7 is minus 1. Okay, so I think this is correct. I'll just check it. Yeah, all right. So now, for the polynomial, how does this work? Okay, there's only one little catch, and this is it. Okay, so let's see. So when you're evaluating a polynomial in a matrix, what is this? So I've got f of a is, and I'm just going to follow the polynomial here. So this is a cubed minus 3a squared. Okay, minus 2a plus 4. No, plus 4 is not going to make any sense. 4 is a scalar. It doesn't have the right dimensions. So you have to remember that this scalar multiplies x power 0, right? So this is, let me put a remark here. This is same as 4 times x power 0, right? Which means that when I'm evaluating at the matrix, it's plus 4 times a power 0. What is by convention a power 0? It's just like for real numbers, it's the 1. But for matrices, this is the identity matrix, right? So, and recall, a power 0 is the identity. Okay, so that's the only catch. So if you're trying to wing this, right, that's where you're going to mess up. Okay, so a cubed we got, it's 26, 18, 27 minus 1 minus 3 times a squared. A squared we've got 10, 2, 3, 7 minus 2 times a. A is 2, 2, 3 minus 1. And finally, plus 4 times the identity. This is it. Okay, I'll just copy this. And go to the next slide, just so I'll just paste it. Okay. Okay, so let's compute this. Let's rewrite it this way. 26, 18, 27. Okay, so this time I'll do it differently from the first time. I'll just keep the minus sign here and multiply everything by 3. So this is 36, 9, 21. Okay, same here. This is 4, 4, 6 minus 2 plus 4004. Okay, and then I'll just write it this way. This is 26 minus 30 minus 4 plus 4. That's the first entry. Then the second entry will be 18 minus 6 minus 4 plus 0. I'll put the brackets after. Cleaner. 27 minus 9 minus 6 plus 0. And then minus 1 minus 21 minus 2 plus 4. And so this is minus 4, 8, 12. Is that minus 16? I think. Doing this in my head, so my head is not working properly today, so maybe that's not right. Let's see. Oh, yes. Got it.
Sir,
Yep.
I'm sorry to come back to this, but it's about 26a. I was just confused about how did you square that, because you said it's rows by columns, right?
Yep. The square?
Yeah.
Yeah.
Exactly.
Okay.
Please.
Okay, I'll do it again. Let's do that again. So A, where are you? 2, 2, 3, minus 1. A squared. This is A times A. That's good? That's good for you?
Yeah.
Okay,
I'm
good.
following.
All right. So now, let's do this guy first. This is row 1, column 1 of the product. So it's row 1 times column 1. So it's 2 times 2 plus 2 times 3. Right? So you have your, let's write it this way. You have your row and you have your column like that. Like this, like this. So it's A times C plus B times D.
Okay, I see.
Yeah. So first entries, you multiply them. Second entries, you multiply them. Third, if there's a third, and fourth. You just keep on going like that, and you'll have the same in each. You just multiply all the corresponding ones together, and you add everything up.
Okay, perfect.
Yeah?
Thank you very much.
All right. Okay. So, all right. So let's move on to number 30. Okay. And I'll end with the sigma notation. Okay, I'll get back to that right once I'm done with the problems in the book. So this is number 30. We're asked to find the determinant of the matrices which are given. So let's just do a few. So A, the matrix is 2, 5, 4, 1.
What's
Okay.
the determinant again?
So, okay. So the determinant is a number that you compute from the entries of the matrix. And so for a 2 by 2 matrix, so let's just, so the determinant of A, B, C, D is AD minus BC. Okay. So you multiply the entries of the main diagonal, you multiply the remaining 2 entries, and you subtract. Okay.
Thank you.
All right. So that's what the determinant is. So once you know that, it's basically a no-brainer, right? The question is, do you know it or not? That's it. So the determinant of this matrix, 2, 5, 4, 1, This is 2 times 1 minus 4 times 5. That's minus 18. That's it. Okay. Let's do okay, well, they're all the same, right? Let's do B. What the hell? So the determinant of 6, 1, 3 minus 2. This is minus 2 times 6 minus 3 times 1. So this is minus 12 minus 3, which is minus 15. Okay, and they're all the same.
Sir,
Okay. Yep.
could you please do the number 32?
Yeah, that's the next one I'm doing.
Oh,
Yep,
okay. Thank you.
absolutely.
Appreciate it.
Actually, that's the one I'm doing right now. Okay, so number 32. Find the inverse.
What's the inverse, by the way? I'm asking a lot of questions. Sorry.
Well, you're basically asking what I'm, and that's fine because I'm going to do it anyway, right? I'm reviewing, so okay. So the inverse of a matrix, a square matrix. So let's say I have. So let's do that in red. So you see that's theory. So I have a matrix, a square matrix. A. So B is an inverse of A if, so think 2 and 1/2. 2 times 1/2 is 1, right? So how you cancel out, when you have an equation, you want to cancel out a coefficient, you divide by that number, right? So, but basically what you're doing is you're multiplying by its multiplicative inverse because they will cancel out to give you 1, and 1 when multiplying by anything just doesn't change anything. I want to do the same for matrices. The matrix that doesn't change anything when you multiply by it is the identity matrix. So the inverse of a matrix is what you use to cancel out another matrix, is to give you the identity. So A times B, B times A is the identity matrix. Okay, so this is what you use to cancel out matrices if you wish. Okay, now real numbers except 0, they always have an inverse, right? If you take any non-zero number, you can always multiply it by something to get 1. For matrices of size bigger than 1 by 1, this is not true. You have non-zero matrices which don't have an inverse, okay? So we saw a criterion to determine which matrices are invertible, okay? So we saw that A is invertible, has an inverse, if its determinant is not 0. And I say if and only if. That's shorthand for if and only if, in the sense that if it is invertible, its determinant is not 0. And if its determinant is not 0, it is invertible. And the way we prove that is by actually computing the inverse. And here's what we got. Okay, so what we got is this. We said, okay, so if the determinant of A is not 0, where the matrix A is, let's say, A, B, C, D, then what is this inverse? So it's a 2 by 2 matrix, but it's multiplied by something which is 1 over the determinant, which is 1 over AD minus BC. So you see that for sure you need this determinant to be non-zero. Otherwise, this is junk. You're dividing by 0. It makes no sense. Okay. Now the matrix, the 2 by 2 matrix here, I have always to think about it. So it goes this way. It's, don't write this immediately when I'm going to write it. I think this should be, so yes, this should be correct. Okay. It's no, it's not correct. What the hell? Let me check that. I have to transpose. So D, D. This should be flipped. And this should be flipped. I flipped everything. What? Yes, this is correct. There we go. That's the one. Okay, so this is the formula for the inverse. Okay, how did I figure it out? Is I know I need to multiply these two things to get the identity. Okay, so let's just go through this again. Let's just, so yeah. Okay, so why? I'll stay in red because it's like theory. I'm not solving the problem here. So if I multiply A, B, C, D times, what did I have? This. Let's multiply those two and see what we get, okay? So this is AD minus BC, right? First row, first column. Then first row, second column is minus AB plus AB. That's an easy one, right? Gives you 0. Let's try second row, first column, that's CD minus CD. That's also 0, which is good. And then finally, second row, second column, that's minus BC plus AD. Okay, so when I multiply those two matrices, this is what I get, which is AD minus BC, 0, 0, AD minus BC. Okay, now if I multiply that by 1 over AD minus BC times this, what happens? I multiply all the entries by that coefficient, so I get AD minus BC divided by AD minus BC. 0 times anything is 0. This is 0. This is AD minus BC over AD minus BC. So what is that? 1, 0, 0, 1, which is exactly what I want. Okay? So it means that if I want to multiply the matrix ABCD by something that gives me the identity, it's what I wrote down. Okay? So it is that matrix here times this coefficient. That's what I want. Okay, I did this in on slides. I don't remember if it was the lecture that I did live or the last one this Monday. I'm not sure which one. I can't remember. Okay, so again, let's go back one up. Okay, so I want, okay, I didn't start the problem, so let's do that. Let's just go now to problem 32. Find the inverse of the matrix 3, 2, 7, 5. Okay. So a better question would be determine if the matrix is invertible, and if it is, find its inverse. So let's start. So is it invertible? So you check its determinant, right? So the determinant of this matrix 3, 2, 7, 5 is 3 times 5 minus 7 times 2. That's 15 minus 14, which is 1. Yes, because 1 is not equal to 0. Okay, so the matrix is invertible. What is its inverse? So let's call that A. So A inverse, that's the notation for A inverse, is 1 over the determinant, which happens to be 1 in this case, times, and let's go back to our formula here, right? So what you do is you flip the entries in the diagonal, and you put a minus, and you multiply the others by -1, okay? So this is 5, 3, minus 2, minus 7. So this is, I'm just applying the formula, that's all I'm doing. 5 minus 2 minus 7, 3. Okay? That's all I'm doing. Okay? So I compute the determinant because in any case, I'll need it for my formula. Okay? So this number here is this number here. Okay? So find the inverse of a 2 by 2 matrix. We have a formula. Okay? So you compute the determinant. If it is 0, the matrix is not invertible. It has no inverse. It is impossible that it has an inverse. If its determinant is not 0, it does have an inverse, and it's given by that formula. And we could check, right? So let's multiply A, which was given, 3, 2, 7, 5, times 5 minus 2 minus 7, 3. Let's just check. So that's 15 minus 14, this is 1. Minus 6 plus 6 is 0. 35 minus 35 is 0. Minus 14 plus 15 is 1. Yep. Again, I should check that the product in the other direction is also the identity, but we know, although this is not an obvious fact, we know that if we do it in one direction, we get the identity, then it's also true for the other. Okay. All right. So let's move on to the sigma notation. So I'm going to do a couple of questions from the problem sheet. So here's one. Evaluate. So this is from problem list. Okay, so number 1 is sum I equals 1 to 5, 2i squared minus 3. Okay, let's do that. Okay, so how does this go again? So you have an index. It runs from 1 to 5. That's the notation, right? You look at the bottom value, top value. It always increases by 1, always. So I goes from 1 to 5, increased by 1. So 1, 2, 3, 4, 5. Then you look at what's inside here, This is what you're adding, okay? So you evaluate it at every single value of the index. It's like a loop, right? So you evaluate this at the values I equals to 1, 2, 3, 4, 5. And the sigma tells you what you're supposed to do with these values. You add them up, okay? So this is equal to 2 times 1 squared minus 3 plus 2 times 2 squared minus 3. So I'm evaluating at 1, evaluating at 2. I will evaluate at 3. The expression, I evaluate at 4, and I evaluate at 5. So this will be minus 1 plus 5 plus 15, yep, plus 29. Please check that I'm doing the right thing.
Oh, excuse me, but what page is this on the book again?
The problem list.
Yeah, just trying to find where this problem is in the book.
Okay, it's not in the book.
Ah.
I added, if you look at let's try this. You see it?
Yeah, I do. Is it on layer then?
Sorry?
Is it on layer then?
Yeah, it's been there since August.
All right.
Yeah. I think I just heard somebody's little brother or little sister. Okay. Let's stop that and let's share this. Yep. Okay, so I don't, whatever that gives you. Okay. Let's try another one. Let's try, okay, let's do number 3. Okay, number 3, you've got the sum j equals 1 to 4 of a to j. So notice now that what you're adding, a index to j, is we don't know what these are. Little daughter. Okay, really? Okay. Yes. Okay. Okay, so A to J, these are, we don't know what the values of these are. We're not given them, right? But again, it's the same thing. So I'm going to evaluate the summand here at all values of the index. Okay, how would we determine the missing values of a vector like in problem 5, what worked 14? Let me finish this problem, then we can look at that, okay? Yeah, so here again, my index goes from 1 to 4. So 1 to increase by 1, 1, 2, 3, 4. I evaluate my summand at all the values of the index. So this is a index 2 times 1 plus a index 2 times 2 plus a index 2 times 3 plus a index 2 times 4. So if I just write it out, this is a index 2, a2 plus a4 plus a6 plus a8. So this is what we get. Now we don't know the values of these. Maybe they would be in some other table, right? We'd have the values of A1, A2, A3, A4, A5, and so on. So these could be the entries of in some vector, for example, right? So you can think of this as like a formula in Excel, for example, right? These A2, A4, A6, A8 might be the values in some column or some row in an Excel table, and you want to add them up, and so, okay. And all the others are pretty much the same. But it's true that it requires a little bit more abstract thinking than the other ones, right? The other ones, once you know what what's the inverse, what's the determinant, you just apply it and that's it. There's really okay, for WebWorks 14, problem 5, WebWorks 14, you'll have to show me, wait, let me see if I can yeah, I think I have it close by. Hello. WebWorks. There it is. 14, number 5. Okay, so I have one in the book which is similar, so I'll do that. Number 22 in the book is extremely similar, so I'll do that, okay? So, number 22. This is page 232 again. So, find x and y if x plus y is equal to y minus 2, 6. Is that similar? It's sort of similar, yeah, it's sort of the same idea, okay? Okay, so I'm given an equation of 2 vectors, okay? And I'm asked to find some unknown values. Okay, so let's just do this step by step. Okay, so we're given that x plus y is equal to y minus 2, 6. Okay, now vectors or matrices in general, when they are equal, what does it mean? It means their corresponding entries are the same. So this means what? It means that the first coordinates or entries are the same. X equals y minus 2. And the second ones are the same. X plus y equals 6. Okay, so if you have an equality of 2 vectors, it means corresponding entries are all the same. They're equal. First coordinates are the same. Second coordinates are the same, and so on. Okay, so what do I have here? I have that x equals y minus 2 and x plus y equals to 6. 2 equations, 2 unknowns, and they are linear equations on top of it. Now, in chapter 10, next week, we're going to see, in theory, how we can solve systems like this with any number of equations, any number of variables, okay? So it could be 12 equations, 15 unknowns. I'm going to show you a way which is pretty easy to solve them. Easy. The algorithm is pretty simple, okay? A very powerful algorithm. By the way, it's used like all the time, everywhere. Yeah. So here, this is a 2x2, what I call a 2x2 system. It's 2 unknowns, 2 equations. In theory, you guys have seen how to solve these, okay? So I'm going to, there are a couple of ways of doing it. The way you've probably seen, I remember the way I like to do it was by substitution. So, so we can solve this as follows. I've got x equals y minus 2. So I'm going to substitute x equals y minus 2 in the second equation. Sorry. Okay. So I get y minus 2 plus y equals to 6, right? By substituting. So that's 2y equals to 8. So y equals to 4. So I've got the value of y. And once I have that, I substitute this back into the first. So x is y minus 2. So I get x equals to 2. Okay. So for problem 5 of WebWorks 14, if I look at it, I have 3 vectors and a fourth unknown vector. Okay, so this, let me add one comment about the WebWorks, which is, so basically what you'll have to do is something that looks like this. It's a bit more involved. You have to do a bit more computations to start with, but here's an extra comment. Okay, so about WebWorks 14, number 5. Okay, so we have a unknown vector x. Okay, it's a 2 by 1 vector, right? This is a 2 by 1 vector. So give a name to the unknown components. Okay, so give a name to its components. So call it, let's say, let's pick something that's not in there. There's U, V, W, and X. Let's call them A and B. Okay. So now you've got 5 times U. I've got 4, 3. You probably have different values. Minus V, which I have is 5 minus 2, plus your X, which is the unknown vector, equals 10x plus W, which in my case is 2, 3. Okay, so you see that you can compute all of this, and eventually you're going to get an equality of vectors. You're going to get, for example, so the values are probably not right, but you get, let's say, something like a 17 minus, maybe something like this. 17 minus a, that's not what you're going to get. You're going to get something that looks like, let's say, 17 plus a and minus 12 plus b equals 10a plus 2. Sorry, running out of room. (10a plus 2 in this case, and 10b plus 3, something like that. Okay, and then the key thing is what I did in the other problem is that 2 vectors are the same if their corresponding components are the same. So this is equal to that, and this is equal to that. Does that make sense, Josh? That either means no or you're gut.
Maybe you went to the bathroom or something real quick.
Yes. All right.
Oh, there he is. He's in the chat.
Ah, excellent. Good. Okay. So so it's similar. So it's a bit more involved, but the thing that maybe helps is, yeah, to give a name to the unknown components of the vector you're looking for, and then you'll eventually play with components. So all right. So that's basically what I wanted to do today. I can send you to wait a minute, where am I? Let's close this. There we go. I can send you to breakout rooms if you want to work on WebWorks, and if you want to ask me questions, I'm around. So yeah, let's do that. And if you don't feel like breaking out, just well, you're free. So 5. What the hell? There we go. So there we go. So if you have questions, just I'll stick around for a few minutes, and
Okay, thank you, sir. Have a good day.
see you.
Sir, if I want to show you the problem on WebWork, do I stick around after the lecture, after the breakout room, or?
Yeah, just stick around. Wait, let me unpin this because I don't even know who's. There you are. Good. I'll let you share.
Okay, so I stay with you. I don't go to the.
Yeah.
breakout room.
Just stay here. I'll stop my share, and I'll let you share your. Let's put this here.